Hi, welcome to our final presentation for ECE67775 Power Aware Acceleration for Audio Equalizer using Cascaded Biquad filters. Our group consists of Arnav, me, Sahil, and Vaishnavi. The motivation for this application is audio processing is necessary in almost all mobile and embedded devices, and it is usually a platform where battery life is critical. CPUs are power inefficient for continuously streamed DSP workloads. Our project seeks to offload these computationally intensive filtering onto an FPGA to explore trade-offs between power and performance. The simplest unit of our project is the biquad filter, or the biquadratic filter. You can think of the biquadratic filter as a reconfigurable filter that can, depending on the input coefficients, can implement low pass, high pass, band pass, notch, shelving, and peaking filters. So any of the standard filters. You can imagine that if you cascade many of these filters in series, you can get higher order filters and get unique kind of noise shaping effects. The biquadratic filter is an IIR filter featuring two poles and two zeros. It is an infinite impulse response, so it utilizes both feedback and feed-forward paths. The feedback path can cause overflow in fixed point designs, and this will require management in hardware. The biquad filter has the following transfer function. This transfer function is typically implemented in two topologies known as the direct form 1 and the direct form 2. It is good to note that there is two other forms called the transpose form 1 and transpose form 2, which are better for floating point designs, which are not very feasible for DSP applications on an FPGA. So back to the direct form 1. The direct form 1 separates the delay lines for both input and output, and because of this, you have more intermediate state registers and a better resistance to internal overflow. The direct form 2 reduces the amount of delay by combining the parallel delay lines into a single delay line for both the input and the output. The trade-off for this is that because there's less state stored, you are more likely to overflow.
The transfer function of a biquad can be rewritten as a difference equation, which tells us how each output sample depends on past inputs and outputs. In direct form 1, a single combined equation can be used, which is simple but it stores more intermediate values. In direct form 2, the computation uses an internal state, W, which reduces the required storage and is more hardware friendly. And since the filter just adds and multiplies, it can pipeline well on an FPGA, and we can run two copies of this filter in parallel for stereo audio with a left and right channel. We start with a stereo WAV file with left and right channels. The ARM processor handles all the file I/O and uses FIFOs to stream samples out to the FPGA. It serializes the samples into an interleaved stream so the FPGA sees them in the order LR, LR, and so on. On the FPGA side, each channel is separated again into its own FIFO and is passed through a cascade of biquad filters. After filtering, the FPGA streams the processed left and right samples back to the ARM CPU. The ARM separates the stream back into two channels and rebuilds the stereo audio file. For design space exploration, we start with the basic floating point implementation. From there, we optimize in two ways, moving to fixed point arithmetic, which improves performance and reduces resource usage at the cost of some precision, and also applying HLS directives to pipeline and parallelize the computation. We then analyze power using the Xilinx power estimator and Vivado, comparing different configurations and seeing how pipelining and cascading filters impact power, performance, and area. Here's the optimized version of the EQ accelerator and the cascaded biquad. We initially tried to pipeline the sample loop with an II of 1. HLS actually synthesized it and it passed COSIM, but during bitstream generation, the design failed routing with bus queue errors, which usually mean the enrolled or deeply pipelined structure created very wide routing paths that the FPGA couldn't place cleanly. And so as a result, we relaxed the II to 2, which still gave pretty high throughput and was able to route properly. To make the pipelining work, we added array partitioning to in and out to split the stereo channels into separate memories so that they could be accessed in the same cycle. Partitioning the coefficient arrays completely also gave each biquad stage the ability to access each of the coefficients at once. And since the number of stages is known at compile time, the stage loop can be unrolled without generating huge multiplexers. And we also inline the cascade function, which exposes the entire loop nest to HLS, letting it schedule work across the stages and across samples instead of treating it as a black box.
Moving to area analysis, this slide summarizes the area usage for different filter configurations. Here, the resource utilization, that is the DSPs, flip-flops, and LUTs, is serving as our proxy for the overall area footprint on the FPGA. On the top left table, you can see how the resource usage scales as we increase the number of stages. The main trend here is that the DSP usage grows linearly, with each additional biquad stage contributing exactly 20 more DSPs. The flip-flop and LUT counts increase as well, but the growth is relatively moderate compared to the DSPs which dominate area for these filters. The bottom table looks at the effect of changing the pipeline initiation interval while keeping the filter order fixed. What we see is that the DSP usage stays constant and that FF and LUT counts fluctuate only slightly. Moving to latency analysis, on the left, I have the compute-only latencies reported by HLS. These numbers represent just the time the accelerator itself needs to process the data without including any communication. The first thing to notice is that the baseline float designs are extremely expensive, but once we apply pipelining, the latency drops dramatically by roughly 10 to 15x from HLS optimizations, and DF2 consistently gives a slight advantage. If you look at the table on the right, these are the real end-to-end latencies measured on hardware, including the ARM to FPGA transfers. And here the picture is very different. The key reference point is the pass-through test, where we send the frames to the FPGA and immediately return them with no computation. That alone takes 257 milliseconds, which essentially represents the communication overhead of moving 5,000 frames across the 254s. As we increase the number of filter stages, the overall design becomes more complex. During implementation, we found that using an aggressive pipelining schedule caused bitstream generation to fail, so we had to relax the initiation interval for larger designs. This naturally introduces a small predictable increase in compute latency. So the main takeaway from these results is that in this system, communication overhead dominates the total latency. That's simply the reality of this particular platform and data movement pattern. Although the runtime differences between the different filter configurations are relatively small, the more meaningful dimension to explore in this project is power, how each design trades off complexity, pipeline structure, and hardware utilization with energy consumption. That's what the next part of the analysis focuses on.
Now I'll walk through the power analysis portion of the project. So for this part, we used the Vivado tool, not Vivado HLS. Vivado HLS, which we've used throughout the class, takes C++ and generates Verilog, and Vivado is one step below that. So it takes Verilog and synthesizes it into RTL, performs optimizations, and then floor plans the design, as you can see in the image on the right. Because Vivado is doing full synthesis, we actually notice some differences compared to HLS estimates. Because Vivado applies its optimizations, one side effect that we noticed is that the DSP usage sometimes changed because Vivado will choose to implement this using lookup tables. And so this was kind of one thing to note as we were analyzing the different power results. We also considered doing vectorless versus vector simulations. Vector simulations would require switching a safe file. Based off of the switching activity of different signals in the design. And so we determined that doing vectorless simulations would be sufficient, but generating these safe files would definitely be a next step for more accurate design or more accurate power analyses. And so there were 3 different axes of exploration that we looked at. One was pipelining, then filter implementation. So as was mentioned earlier, direct form 1 versus direct form 2. And then the number of stages. So these are kind of 3 axes that we looked at. And then on the right-hand side, you can see what the kind of Vivado GUI looked like as we were completing these different power analyses. So let's look at the results now. Across all filter orders, increasing the initiation interval did cut power. With both implementations of the filter. The biggest drop was going from initiation interval of 2 to 4, and after that you'll still get a decrease in power, but not as significant as a drop as going from that 2 to 4. And so this kind of design space sweep would be pretty valuable if you wanted to choose an implementation on a tight power budget, or if your application needs a certain amount of attenuation. So you could compare the different stages, indicating, a different order of the filter and different attenuation. So overall, this design space sweep would be pretty helpful to choosing an implementation. Some kind of more general insights about each of the three axes. In terms of pipelining, Direct Form 2 has a little bit more power overhead. And at a higher initiation interval, that power overhead is actually matched by Direct Form 1. And that's because of more registers that end up having a lower activity factor. In terms of the filter implementation, the Direct Form 1 was more sensitive to changing initiation interval, whereas DF2 had a more compact architecture, so that kind of led to a more stable power profile. And as you increase the number of stages, you'd add about 0.03 to 0.05 watts, obviously depending on what the pipeline and optimization is of that stage. But overall, those were kind of some of the main insights that we saw on each of those axes.
So for this demo, we have an example of how this filtering system could be used in practice. This is something that's called a cone filter, which is 3 cascaded biquad filter. If you look at the transfer function, there's a ton of peaking at equal frequencies, and the result of this type of filtering will make the input sound very metallic, hollow, and with a ton of echoes. So here will be the input wave.
This is my voice on the left. This is my voice on the left-hand side.
And here will be the effective output voice.
This is my voice on the left. This is my voice on the left-hand side. This is...
So that is a demo, and thank you for watching.